Yes, so for the n volume, what it is going to look like. Okay, so let me just first write function f. It may be a function of f1, f2, x1, x2, let's say xn, right? So we're gonna have this n integration. Okay, so we have n integration, right? And we're gonna have this n volume, which is dx. Okay, so what instead we can just do like this. Okay, so this is the this symbol. This is not a pi, actually this is the multiplication of the function 1 plus del f by del x I, and I moving from 1 to n, and we're gonna have this dxi. Okay, yeah, or we can also write like this. Instead of this multiplication sign, 1 again for 2, 1 plus del f by del x n dx1 dx2 dxn. So these two are the same. Okay, so this is the case for the n dimensional, or we can say the n integration. Now we will start our topic, which is relevant to our electrodynamics series, which is the integral calculus, right? So here we will study three main topics, which are the line integral, surface integral, and volume integral. Okay, so we will divide this topic into the two. Okay, first of all we will divide it. First is the line integral, surface integral, and volume integral. And the line integral. Okay, so let's begin with the line integral. It is sometimes also called as the path integral. So what is that? Let's do this. So we have this x, y, and z axis, and we have one curve, right? So line integral. Okay, and let's say that this curve began at point A to B, right? And this A and B may be a vector. Okay, so it is the more clear picture would look like this. Let me redraw it. So again we have this x, y, and z axis, and let's say the curve began over here. So this is the A, the position vector where this curve began, and we have a vector B, the position vector where the curve ends. So the line integral is okay. So line integral is, let's say, so how we take the line? Well, line integral can be taken by line integral is actually we take the line integral of a particular let's say vector function, right? So it may be some function, or maybe in general it is a field, right? It is a vector field. So let's say we have a vector field v. The line integral is the integral of the dot product of that with the infinitesimal displacement vector from a to b. So this v is a is a vector field that is spread in this space, right? So if this v may be something vx may be a function of x, y and z and along the x, and similarly v by x, y and z along the y cap plus vz x, y, z, z cap, right? So if we draw it, it may look like this, that I have already drawn this kind of function in space. So it is several vector fields that is spread all over the space, and we represent it by arrows, the different directions and different magnitudes of arrow. Okay, so we can just expand it. It's vx x cap plus vy y cap plus vz z cap. And what is this dl? This dl in the Cartesian coordinate is dx x cap plus dy y cap plus dz z cap, right? So line integral will be this d will take the dot product of these two things. So it is going to be vx dx plus vy dy plus vz dz. Okay, from vector a to from position vector b. So we have three variables over here, and we have only one integration. In the last video we have seen that for the three variable we're gonna have this triple integration, but here we don't have this thing. So why is that? Because we have this line. Okay, so in the last case, when we have this line in the last video, when I draw the line and calculate the total length of the line, this function f is the only function of x. That's why we're gonna have only function of x, right? So that we are able to calculate it, and the integration will have this some term times dx. Okay, here this curve is moving in all this space. I mean, it is not restricted to a plane, it's move in a space. Okay, so as the curve moves, all the variables x, y and z, all the three variables are changing. That's why we have this terms like the dx, dy and dz, but here only the x is changing. Okay, now this is the first thing. That's why we're gonna have this dl, which is the infinitesimal displacement vector, right? So why don't we have this the surface integral, the double integration over here? Because this is only a curve. If it would be a surface, then we're gonna definitely have this this double integration, right? So how we will solve this? Well, it can be solved because that curve is itself is gonna have an equation, right? It's gonna have two equation. Okay, so a curve in two dimensions represented by y equal to mx plus c, right? We are not going to do this at this time. What we are going to do, we are taking a parameter which defines this curve. Okay, so we'll write the parametric equation of this curve. Okay, so that curve have parametric equation where x is equal to so x is going to be x, some let's say parameter lambda, y is going to some parameter lambda, and z is going to some parameter lambda. So what we will do is take the derivative, and here we get some terms times d lambda. In a similar way, dy will get again some term, will d lambda and again this term d lambda.